Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm happy to introduce Nilesh. He's a PhD student at the University of Washington. His advisor is Dan Suchu. He even visited us in the summer of 2004, I think. He's done some pretty foundational work on managing uncertain databases, and he's going to tell us a little bit about that. He's in fact even given a tutorial at Sigmod on this. So he's going to tell us more about what he's done. Over to you.
Thank you for the kind introduction. I'm really excited to be here and to present to you my work on managing uncertainty using probabilistic databases. So let me start by giving you a very simplistic view of a database. There are queries, there are facts, and you get answers. But I want to point to you the three basic assumptions that went into the design of a database. So the facts, they are very precise and they are all correct facts. The queries, they are rich and structured, but they are very precise. And the answers are what you get by logical implication from the facts. So when databases were designed, the applications in mind were inventory and payroll, and this model has served those kinds of applications still well over the past couple of decades. But now there is a whole new set of applications which are emerging, which challenge some of these basic assumptions of databases. What do these new applications look like? So these applications, they work on a large number of rich and heterogeneous data. There's so much structured data on the web, and there is a constant push towards adding more structure to the data. And the applications that are trying to work on this data, they have to deal with the problem of heterogeneity. There's also a push towards automation, and we're using more and more machine learning algorithms for our data extraction tasks, which include extracting information from text, matching schemas of different databases, and linking the records among different databases. And all of these applications, they give you answers with certain confidences, and the data they produce is uncertain. So users, they often find themselves writing queries over data which they did not create, and they cannot exactly specify the query over such databases. And in the presence of so much uncertainties, users want not a set of answers, but a ranked list of answers based on relevances. It's a model being popularized by the search engines today. So you see, there is uncertainty in data, in queries, in query answers, and the traditional model of databases based on logic is inadequate to deal with these issues. So I'm going to give you an example of two applications that to illustrate these issues I'm talking about. The first application is a movie query engine, and the objective here is to allow users to write queries jointly over three different data sources. And so here are the three data sources. There is an internet movie database. It is a large and extensive collection of structured data about movies and actors and directors. There is Amazon movie DVDs. So you can go to the website and you can find information about all the movies and their DVDs and prices. And there's a web service that actually allows you to access all this data. And then there's this Usenet newsgroup postings. So there's a huge collection of text files containing reviews of different movies. And you want to build a system where you can use all this data to write queries. So how do you go about building such a system? So you have this IMDb database. It's in relational format. You can just load it into the database. With Amazon, you have to do some more work. You have to write some web service wrapper, but you can extract all the data. You can load it into the database, into a few tables. With the newsgroup reviews, you have to do some more work. You have to use some kind of information extractor that extracts the name of the movies from the text. And then you have to use some kind of a classifier that looks at the words in the text and it tries to find the polarity of the review, whether it's a good review or a bad review. So you have all this data, you load it into the tables, and now you can write queries. For instance, you can say find DVDs of movies which are highly rated by Arnold Schwarzenegger. It's a query that involves all the three databases. So far so good. You have this data, you're writing queries. The problem is the queries don't return any answer. And there are lots of reasons why this happens. So if you look inside, the IMDb database and the Amazon database, they represent movies differently. So the same movie may be represented in different ways in the different databases. And you need some kind of a machine learning algorithm that tries to look at all the evidences and tries to find a confidence for each pair of movies. In fact, when we did an exact search, we found out that 30% of the movies were represented differently in the two databases. So next, if you look at the information extractor, it's going to produce things with errors. It's going to miss certain things. It's going to produce some things which are incorrect. It will have confidences associated with each extracted name. And then the classifier, it's also probabilistic. So it's going to give a probability associated with each review, whether it's a good review or a bad review. Then you need to match the movies from the IMDb database and the Usenet database. So that's another source of uncertainty. And finally, when you look at the query, the terms in the query need not be exactly the terms in the database. And therefore, you again need some kind of a matching to match the keywords in the queries with the database. So there's this whole, in the whole system, you see there's so many different sources of uncertainties which you need to model, and you need some kind of a logic that allows applications to just store all these uncertainties and allow users to write queries. Here is a totally different application. It's about analyzing the data privacy. So let's say you're a medical agency and you want to publish a data about your patients for research purposes. At the same time, you want to make sure that you're not disclosing any sensitive information about any individual. So you will try to anonymize the data. So you will remove the names. You will just publish, let's say, age, weight, zip code, and disease. And you may want to hide some of the values if you think they are sensitive in disclosing the information about any person. And then an attacker comes and tries to find out the diseases of individual persons. And the attacker may go and find some public database, maybe from the voter registration database, and the attacker finds information about individuals along with, let's say, their age, smoking habits, and zip code. Now, you may want to join these two databases to answer the queries you want, except that you cannot do it. There is no column to join on. You can join on age and zip code maybe, but there is no unique identifier. However, the attacker knows certain other things. For instance, there are some statistics which the attacker may know. Like maybe the expected number of patients in each zip code is 5. Or maybe a smoker is much more likely to have lung cancer. So using this statistics and the facts, the attacker may try to guess which person has which disease. And here the problem is, how do you quantify the uncertainty in the query answers based on the statistical information? This is an application where uncertainty is good because it's preserving the privacy of individuals. But we need a way to quantify the uncertainty. And there are several other applications. So there is scientific data integration, there is sensor networks, there is personal information management. All of these applications have uncertainty as a fundamental problem. And it appears in various different forms. There are inconsistencies, there is incompleteness, and there is statistical knowledge. So what we need is a framework that can represent these different kinds of uncertainties and allow the users to query them. In this talk, I'm going to propose a probabilistic framework with the goal of a uniform representation of probabilities. And there are three issues that I'm going to talk about. So how to define the semantics for probabilistic databases? Traditional databases were based on first order logic, but what kind of logic do you use in such a database? How do you represent the uncertainties in different sources in such a system? And most importantly, how do you answer queries efficiently? So this is going to be the three main topics of my talk. So let's start with semantics. I'm going to define a very clean and simple way to think about probabilistic databases. So a probabilistic database, it's simply a probability distribution over all possible databases. And any database with positive probability is called a possible world. So this is the possible world semantics, which is widely used in knowledge representation to represent uncertainty. And here's an example. So there are 4 different. So this is a probabilistic database with 4 different possible worlds. These are the 4 tables. Each of them has a probability that adds up to 1. And So the possible worlds are these 4 tables. How do you define queries over such a database? Well, the answer to a query is a set of tuples along with probabilities. And to find the probability of a given tuple, you use this expression, which says that you evaluate a query on all possible databases. And you look which of them give you the tuple as the answer, and you add all the probabilities. And that gives you the probability of the tuple. Let me give you an example. This is a database with 4 possible worlds, and the query is written all years that have both a high and a low rated movie. So if you execute it, you get the following 2 answers. Let's look at 1972. In the first instance, it appears with both a high and a low rated movie. Same thing with the second instance, and that's only 2 instances. So you add the probability of the first 2 instances, and the same thing with the other year. So to summarize the semantics, it's a very clean and simple way to think about probabilities. Every query has a well-defined semantics, no matter how complex. The problem is there are too many possible words to so we need a good representation to store all the possible words.
So the output of a query is not a probabilistic database. So a set of tuples with probabilities, so they're different than a probabilistic database.
Right. Yeah. So the idea is to. Well, the idea is to present to the user the most relevant answers.
So you have relevance is the main motivation.
Yeah, the main motivation is for the users to find the most relevant answers given the uncertainty in the input. So next I'm going to talk about representation. And a simplest way to represent a set of possible words is using a tuple independent database. So this is an example. There are 2 tables, and every table has a new column called probability, which shows the probability of that tuple being correct. And all the tuples are independent. So given such a database, you can generate all possible words, and this is how you do it. So I'm looking at a single table. So every subset of this table is a possible word, and you can derive the probability from the input probabilities. So in this table, there are the P1, P2 is there, and P4 is there. So its probability is P1 times P2 times 1 minus P3 because it's not there times P4, and you can get a probability for each possible word. So that defines a possible word database from the tuple independent database. And given that, all the queries have a well-defined semantics. Well, before I go into query evaluation, let me give you an example, an application of this representation. So let's say you want to build an application that supports queries with similarity predicates. And you assume all the data is deterministic. So you have these 2 tables, cast and films. All the data is deterministic, but you want to support queries like this, which says return all the films where the actor name is similar to Kevin and the title is similar to Rain. So now you can look at these predicates and you can apply them to the tables. So you look at each cast and you see how well the actor matches the Kevin. You use your favorite algorithm to match them, and then you get these confidences with each tuple. And you apply the other predicate to film, you again get a set of probabilities. So now the resulting database, you evaluate the query in the resulting database to generate a set of answers with probabilities. And this gives you a way to define semantics for any complex SQL query with similarity predicates. So the problem is, given a tuple independent database, how do you evaluate queries? And you don't want to construct all possible words to evaluate this, which would be exponential. So before I go into that, let me give you a bit of a history of the problem. It's a problem which has a long history, and people have been looking at this for more than 20 years, and yet it was not a very well understood problem. So let me give you some of the approaches which people have considered. Some systems, they only support a restricted set of queries for which they know how to compute the answers. Some systems use exponential algorithms, and in the worst case, that amounts to constructing all possible worlds. Some systems just compute the bounds on probabilities without actually giving any guarantees. And then there are some systems that use ad hoc semantics, which is very specific to a given query or a given data. So what is so hard about query evaluation? Let me give you an example. I have these 2 tables, a film and a cast, along with probabilities. and I want to answer this query, which says, return all the years in the film table which have a matching movie in the cast table. So you see 1995 has this movie F1 that appears here. 1982 has a movie F2 that appears here. 1971 does not have any matching movie. So if you evaluate this query, you will get these two as the answers. The question is, what is the probability? Let's look at 1995. For this to be the answer, this tuple P1 has to be in the database. And at least one of this Q1, Q2, Q3 had to be in for the film ID F1 to be in the database. And if you compute the probability, you will get this expression, which is P1 times the probability that at least one of these three is there. And that gives you the probability for 1995. With 1982, it looks much more complex because 1982 appears twice in this table. So the point is, these expressions can get very complicated, and the question is how do you compute them in general, given any query and given any database. So before I go into that, let me give a brief history of how you do it in a traditional database. And you use it using relational operators. So you have a join operator that takes two tables, and it computes for each pair that have the same join attribute, it computes an entry in the output table. And there is a project operator that just takes a set of a table and it just removes a certain attribute. So in this case, it removes the actor attribute, and as a result, several tuples they collapse into a single tuple. So now let's try to extend these operators to also compute probabilities. And here's how you may go about it. So if you're joining two tuples, you compute a new probability which is just their product. And if you're doing a projection that collapses several tuples into the same tuple, you just use this formula which is the probability that at least one of them exists. Now this is just a heuristic because it's assuming that the input these operators have independent tuples. Now although you may start with your database which is independent, as you're computing these expressions, they can have very strange correlations. And so this approach may not always give you the right answer. But let's see how well it works. So this is the example that I considered before. I have simplified the table to just contain a single year. And the answer to the query, as we recall, is this expression. Let's try to compute this using relational operators. We start from the two tables. You join them. You get three tuples along with the probabilities which are their product. And then do a projection of the year. You get this single expression. Except that it's wrong. It does not match with the answer which we evaluated before. So what went wrong is, so our assumptions about independence did not hold at each intermediate level. And therefore, this plan, it gave you a wrong answer. But let's not lose hope. Let's try a different plan. So you start with the two tables. You first do a projection to just compute the film ID in the cast table. And then you join it with the other table. And then you get the same answer, but this time with the right probability. So this shows that two different plans can give you different answers. Sometimes they can be right, sometimes they can be wrong. Here you can prove that this plan on the right, it always gives you the right probabilities no matter what the input database is. And we call such a plan a safe plan. So the question is, given any query, how do you check whether it has a safe plan? And what do you do if the query does not have any safe plan? Let me answer the first question first. So given any query, how do you compute a safe plan? And for this, you need to express the query in the conjunctive form. So there's a query which has three relations, movie, actor, and director. And there are four attributes, title, actor, age, and director. And you want to check whether there's some values of these attributes that make each of these three predicates true. So given such a query, to compute a safe plan, you start from a graph. Its nodes are all the relations. And its edges, it's a hypergraph where the edges, for every variable here, there's an edge containing all the relations having that variable. So if you look at title, it just appears in movie. So it's an edge containing just movie. The age, it just appears in actor. If you look at actor, it appears in actor as well as movie. So the edge contains both the relations. And the director just appears in this relation. So you build this graph. This graph has a very nice property. So given any two sets, they're either disjoint or one is completely contained in another. We call such a graph a hierarchical graph, and we say that the resulting query is hierarchical. And given such a query, we know how to compute the safe plan. And it is as follows. So you work top down. You look at the whole graph, and you build a plan recursively top down. So this graph has two components. So whenever you find two components, you make a join. The right side would be a plan for this component. The left side would be a plan for this component. So then you go into the right side, and this has a single component with top attribute director. So in that case, you do a projection that removes that attribute, and then you go inside. That's the rule. So then you go to the left. It has a single component with actor as the top attribute. So you remove that attribute and you go down. Now there are two components, so you do a join, and then you go inside each one of them. So you find a plan. And you can prove that this plan will give you the right probabilities no matter what the input database is. And this is the way you can compute a safe plan for any query. Here's a different query. It also has three relations, actor, movie, and director. Let's try to make the graph for this query. So the actor attribute, it appears in the actor relation and the movie relation. And the director attribute, it appears in movie and director. And here you see this graph is not hierarchical because there are two sets that intersect, but none of them is contained in another. And here you can prove that there's no safe plan. So given there's no way you can compose these operators to give you the right probabilities in all cases. Well, you can still ask, can you add some new operators that would give a plan for this graph? And we answered that negatively using this following result. So we show that for every simple conjunctive query, one of the following holds. So either the query is hierarchical, in which case its complexity is in p time, and I in fact give you the algorithm for computing it. You first find a safe plan for it, and you execute the plan. And that gives you a p-time algorithm to evaluate the query. But the other case is when the query is not hierarchical. In that case, you can prove that the complexity is sharply complete, which means there's no way you can evaluate it in p-time unless p equals np. So no matter how many operators you add into your algebra, you will never find a plan for this query. Okay, so such queries do occur in practice, and what do you do about them? We have two techniques to take care of them. So the good news is these queries are easy to approximate, and in fact, there is an algorithm that approximates it to any precision you want in polynomial time, and it uses a Monte Carlo simulation technique that just simulates the database and tries to estimate the probabilities. We also have a variant of this technique to just compute the top k. And here the idea is the user is not interested in the exact probabilities. The user wants the top k answers which are most relevant to the user. And in that case, you can optimize the algorithm to just compute the top k without actually spending lots of time finding the exact probability of tuples in the bottom, which are not going to make into the top k. And that speeds up the algorithm by at least a fact on the order of magnitude.
So in top k, you need to find out the top k highest probability?
Right. So, yeah, the most top k tuples with the highest probability. Okay, and so far I have only discussed databases where all the tuples are independent. I will talk a bit about correlations. So one natural way to represent correlations is using independent and disjoint tuples. And here's an example. So here the tuples are divided into groups, and these two tuples form a group, and all the tuples here are disjoint. So it says either Kevin Bacon lives in Seattle or in LA, but not both. And so these are not independent, but these are disjoint events. And this is another group where both of them are disjoint, and across the groups are independent. This representation comes very naturally with inconsistent databases, where you have two contradictory facts, and you don't know which one of them is true, and you want to store them as exclusive events in your database. And we have techniques to evaluate queries, and we have safe plan algorithms for this representation. Another way to express correlations is using conjunctive views. So you start from a set of tuples which are independent and disjoint, and then you express correlations using conjunctive queries themselves. And you can show that this is, using this representation, it's a complete representation. So you can store any probability distribution over databases. And in fact, for many applications, there is a very natural way to represent the correlations in this form. I don't have, I will skip the details here.
May I have earlier you said the query result itself is not a probabilistic database, right? The probabilities that you get for the query result are not in the same representational model as the original database. So, but here you're saying something different.
Well, the query results, they are not, it's a database, it's a probabilistic database, but it may not be a tuple independent database. So if you start from a set of set of tables which are independent, you write a query, and then you will get a new table. The tuples there will have very strange correlations. And in fact, we can show that you can capture all possible correlations by using queries.
Do you know what kind of correlations they have? It's one thing to say, okay, I can capture all possible correlations, but given a query, what is the kind of correlations that those tuples have? The tuples in the result have?
Well, the query defines the correlation. The query defines the correlation. And for many applications, the process which generates the data is itself a query. And you can start from some basic independent events, and you can write these queries that capture the data generation process.
So does it mean if I take a pair of tuples in the query result, and if I want to know, I don't know what does it mean to say what's the correlation between the pair of tuples in a query result? Can I get some, how are they related, or how?
You can just ask what's the probability that both of them are true.
I see. Yeah, that's.
And you can answer that query by looking at the query that generated those tuples. Yeah.
What happens to all your complex results in these alternate representations? Because I'm assuming that your earlier results were for independent.
Yes. So we have results. So we have a dichotomy result which shows that every query is either p-time or Shapley complete. The boundary is different. The boundary shifts. But we again have so the Monte Carlo simulation technique, we extended to this representation, and the safe learn technique will also extend to this representation. And for the conjunctive views, you can actually just compose your query with the original query, and then all the results follow.
Compose which query?
So given any user query that you want to evaluate on this representation, you can just compose the user query with the queries that generate the data. And then you can just use the existing techniques to evaluate the query.
But won't this composition kind of show up the size of the probability? I'm not sure. Sorry.
We can talk about it. Yes. So let me move on to statistics. So I showed you the other application where you want to use statistics to find the probabilities of certain queries. So statistical knowledge, it's just another kind of uncertain knowledge. And here the challenge is, how do you even define the semantics of queries? And then how do you answer queries efficiently using statistics? So let me give you an example. Let's say you have a relation containing names and phone numbers. And let's say you know the size of the domain for the names and phone numbers is n, which is a very large number. Think of all possible names in the universe and all possible 10-digit phone numbers. But you also know the following statistical knowledge, that the expected size of the relation is 50. And now, somehow you figure out that the person John is in the database. And separately you figure out that this phone number 1234 is in the database. So you can express it using the following conjunctive query, which says that John is there and the phone number is there. But now you want to answer the following query. Does John have the phone number 1234? And here you would expect the answer to be true with probability 1 over 50, because you believe there are 50 tuples in the database, so there is around 1 over 50 probability that these two facts are talking about the same tuple. So how do you generalize this intuition to define the semantics for answering queries with statistics. And here we use a technique called Bayesian analysis from AI, which says that given the statistics, you generate a probability distribution over all possible databases, which captures your belief, and it's called the prior distribution. And then the probability of Q over this distribution is the prior probability that you believe the query is true. And the probability of Q given V, it's the probability of the query being true after you see the observed facts. And the difference between these two probabilities, it gives you an information, it gives you a measure of information which the view discloses about the query. The question is, how do you use statistics to generate a prior distribution? And here we observe that each statement of statistics is in fact a statement on the probability distribution. So when I say the expected size of the relation is 10, I'm saying that if you look at this distribution, this distribution, and you compute the expected size over all databases, you should get a value 10. So every statement, it imposes a constraint on the distribution that you can use. And you want to choose a distribution that satisfies all your statistics. The problem is this set of constraints need not uniquely define a distribution. So here we use another technique from knowledge representation called the maximum entropy principle, which says that among all the distributions that satisfy your statistics, choose the one with maximum entropy. And the entropy is a measure of the randomness of the distribution, and this gives you a distribution which is as random as possible, but that still satisfies all of your statistics. Let's go back to our example and see how the semantics work on this example. So you have the statistics that the expected size is 50, and you see the following two facts given by V, and you want to find the probability of this query Q. So first, let's look at the maximum entropy distribution given the statistics. And it's a very simple distribution. So the domain size for names and phone numbers is n. So there are n square possible tuples in the universe. You pick each one of them independently with probability 50 over n square. And then you can easily see that the expected size of such a distribution is 50. And this is the one that maximizes the entropy. So now let's look at the probability of the query on this distribution. So if you just look at the query, its probability is it's something which is 1 over n, where n is the domain size. And if you assume that the domain is really large, then this goes to 0 as the domain goes to infinity, which is very intuitive. It says that if you don't know anything about the database, then the prior probability that this query is true is 0. But if you look at the conditional probability of query given the fact, it converges to a value which is 1 over 51. So it says that even though you may have a really large domain, once you see the following two facts, that the John and the 1, 2, 3, 4 is in the database, the conditional probability of the query being true is 1 over 51, which is not 0. And so the question is, how do you evaluate queries given a bunch of statistics? And here we found a very interesting connection to random graphs. So the distribution which I just showed you, it's precisely the Aidy-Shreni random graph which has been widely studied in the graph theory. And then the query evaluation over using statistics, it just amounts to computing conditional probabilities over random graphs. And in fact, we got some new results on the existence of conditional probabilities and some complexity bounds for computing them over a class of random graphs. So far I showed you the theory behind a probabilistic database. Let me describe to you some of the systems that we built and our experiences with it. So one of the systems that we built is called Mystic. It's a general purpose probabilistic database system that allows you to store probabilistic data and query it. It has a query language which is SQL, but it's extended with a few operators to allow similarity predicates. And then it has a data definition language that allows you to describe the uncertainty in the data. And it's built on top of a standard relational database. So it takes user queries, it compiles them into standard SQL queries, and it just executes them in the database. And it embeds all the probability calculations into SQL queries. Let me show you some of the features Mystic has. So you can have probabilistic tables in the schema, and you can describe which attributes are probabilistic and whether they're independent or disjoint. The sequel has the following two new constructs. You can say name is similar to Kevin, and you can also associate a confidence with each predicate. So you're saying that maybe I'm completely wrong, maybe the name is something totally different, and I have only a certain confidence on a predicate. So these are two semantically different constructs which are treated differently. You can also describe statistics. So you can say every age and zip code has around 10 names. And then you can have a probabilistic views. So you can say, you can just write any SQL query you want, and you can just store them as a new view. And the users, they can just use it as a new relation in writing their queries. And here we have to be careful, because we cannot just store the output of the query. We also have to store the exact query that generated the output, because the output will have some correlations, and this query describes what those correlations are. So Mystic was developed in collaboration with lots of people. So the movie application I described to you in the beginning, we actually implemented it on Mystic, and we demonstrated it in the SIGMOD conference. Let me describe to you another system which I'm working on currently. It's a system for biological data integration that integrates 12 different public databases containing information about proteins, genes, and diseases. And here is the query model. So the scientists, they don't want to write SQL queries. They want to browse the data starting from a very simple query. Here is a snapshot from the system. So you start from some query. Maybe you're looking for some specific tuple. Let's say the breast cancer gene. And then the user, it can click on any node, and that joins the node with other databases. So maybe you're looking at the same gene in a different database, or maybe you're looking at a disease associated with that gene in a different database. So you can click on node, and that will expand it by joining it with other data sources. And you can keep browsing multiple data sources using this way. The problem is these links have to be approximate. So let's say you have a protein and you want to find the same protein in a different database. Well, no two databases write proteins in the same way. And you have to use some kind of a sequence alignment algorithm that matches to proteins. And you sometimes will find a good match, sometimes you'll find not so good match. The same diseases, they're written in different ways, so you'll have to use some string predicates to match diseases, and so on. And also, different data sources, they contain information with different reliability. So there are some data sources which are very authentic and which contain all the accurate information. There are some databases where anyone can go and add their experiments and which are not very reliable. So the scientists, they want to make sense out of their browsing in terms of the links they're following and in terms of the data which they're getting. And here's actually a snapshot of the system with just two-level complete expansion. And you see that there's no way you can make sense out of this information simply because of the number of data sources and the approximate matches across these data sources. So our approach is we associate certain uncertainty matrices with each of the data source and with each link between two data sources. So that gives you some kind of a confidence with each node and each edge in your browsing graph. And then we use the probabilistic query semantics to find the relevance of each node to the user. And we present these nodes to the user in the decreasing order of relevances to guide their browsing search. So this is a project that I'm doing in collaboration with the medical school at Washington, and with there are many collaborators. So we built the first prototype of the system and we showed it to the scientists, and we got some very encouraging feedback. Okay, let me give you a conclusion. So let me give you a summary of my results. So I defined a probabilistic database as a framework to manage uncertainty in different applications. And I looked at a representation of database with explicit probabilities. And here the main result was a dichotomy theorem which said every query has a complexity which is either p-time or Sharpie complete. For the p-time queries, I gave a safe plan algorithm to evaluate them. And for the Sharpie queries, I gave a Monte Carlo simulation to evaluate them approximately. And then we considered several extensions to the model to handle correlations. I also looked at statistics, where we found very interesting connections to random graphs, and we found some new results on the existence of computing probabilities and the complexities for computing them. And then we build systems, Mystic and U2. So now there is lots of excitement in the community about probabilistic databases, and these are some of the projects currently going on in various research groups that look at probabilistic data. Let me also describe to you some of the other work which I did. I did some work on query optimization, where I looked at optimizing multiple queries at the same time, trying to exploit their common sub-expressions. I did some work on peer-to-peer databases, where I looked at efficient indexing schemes to answer queries efficiently. I did some work in machine learning, where I looked at the problem of classification in the presence of an adversary who was trying to fool the classifier. And then I did some work on user preferences in database queries, where we looked at ways to estimate the cost and cardinality of such queries. Let me also describe some of the problems that I want to work on. So I think databases and AI, they have walked on different paths for a long time, but it's time when they should come together. So there's so much research in AI on managing uncertainty. There's so much research in databases on scalability to large data sets. And we need techniques that can manage uncertainty and scale to large data sets. So some specific questions are, can we actually incorporate the graphical models in AI into databases? And can we in fact use databases to speed up the inferencing in AI algorithms? There are some specific problems I want to work on. Aggregates over queries. It's a very challenging and very important problem. It has applications in privacy preserving data mining, where you look at lots of aggregates over your data and you want to reason about the original data that generated it. And there's also applications over online analytical processing over uncertain data, where you want to compute certain aggregates for making decisions. I also want to look at constraints over probabilistic databases, which again has lots of applications. In data exchange, constraints are often used to describe mappings between two different data sources. And if you have an uncertain data and you want to map it to a different schema, how does this translate in terms of the constraints? It also plays an important role in data cleaning, where you have some dirty data and you think certain constraints hold over the data and you want to reason about that. And finally, I want to use all this machinery to build new applications. There are some very important applications like personal information management, scientific data integration, where uncertainty plays a very fundamental role. And each such application will bring certain issues that I want to look at. So to conclude, I would say that the next generation of database applications have uncertainty as a fundamental problem, and a probabilistic database can provide the platform that can drive these applications. That's the end of my talk. Thanks.
Yeah. So you said you worked with a couple of applications in the Mystic and the other project, right? So in sometimes the effectiveness or usefulness of this framework is somewhat based on how accurate, how good the input probabilities are, right? In those two examples, what was your experience and how difficult it was to get the right probabilities as input?
So in these applications, some of the probabilities came from machine learning algorithms that used a probabilistic model to find the probabilities. And some of the probabilities just came from the users. For instance, some of the databases, in fact, have a rating between 1 and 10 of how reliable the experiments were. And we used some simple heuristics to convert them into probabilities. Our experience is that the answers we get are pretty robust to variations in the input probabilities. So if you have...
How do you evaluate that? So was there some methodology to evaluate that it was effective or not effective?
Right, so we have played with some synthetic data where we have looked at the precision and recall of our system based on input probabilities. But what we need is some kind of big user study that can really evaluate such a system. The main problem is there's no labeled data set out there where we can just evaluate our system. There are so many data sets for machine learning algorithms, but so far there's no data set for a probabilistic database. We had some anecdotal experiences with scientists and when we demonstrated our system in the conference. But at some point, I would like to have a benchmark where different systems can actually evaluate their precision and recall.
I have a question. So you mentioned this scaling up is important. Have you tested how well your algorithms for query evaluation scale?
Yeah, so the movie application that we built on Mystic, the total database size was around 500 megabytes, and some of the complex queries that join more than 2 tables, they ran under a minute. So I showed that the 2 kinds of queries, the p-time and the Sharpie complete queries. The p-time queries, they don't have any overhead over traditional queries, and they actually run pretty fast. The Sharpie complete queries, they are an order of magnitude slow, but they still ran in under a minute for a half a gigabyte database. And if you want to do optimizations like top K, or you can actually compute some sub-queries which are safe plans, and you run a simulation on top of it. So with these optimizations, you can actually speed up the queries.
The question?
So the complexity results that you have is a function of the schema, right? It's at the schema level. I can look at a query and then answer if it can be answered in a safe way or not.
Okay.
But have you also considered instance level, like as an exaggerated example, if every tuple has probability 1, you can answer everything in a safe plan. So it might happen that your 85% of your tuples have probability 1 and a very small fraction have probability. So it's possible that you can have this entire slew of techniques that look at the actual probabilities and not at the schema of the uncertainty.
Yeah, that's a good question. And there are 2 ways you can go about it. So you can use some constraints on the database to describe some additional properties that your database satisfies. And then you can use it to find safe plans for queries which did not have safe plans. Like for instance, we do take care of the functional dependencies and key constraints in the database to actually compute safe plans for the queries which did not have safe plans otherwise. So that's one way to go about it. The other way is you look at each of the tuple and all the tuples that generated that tuple. And for some of the tuples, it would be very hard to compute the probability. For some other tuples, you can compute it by just observing that all the input tuples had probability 1, or if you get a very simple expression. So you can do a fine-grained optimization where for some tuples you compute their probabilities directly, and for some tuples you do a simulation.
Thanks, Nilesh.
Thank you.